Doesn't matter.
Right. Next speaker is another Schrodinger's colleague, Stephen Albanese, who will be sharing his work with us today. Thanks.
Great, thanks, Dima. My name is Stephen Albanese. I'm a member of the therapeutics group at Schrödinger. And I first want to thank the conference organizers for the opportunity to speak to you today. The work that I'm going to share today is a case study from one of our active drug discovery programs, where we took free energy calculations and structure predictions, and we moved them beyond on-target potency predictions, and tried to use them to address an ADME liability that we ran into in lead optimization on this project. And thanks to John, wherever you are, for highlighting how hard this is for drug discovery, because it sets the stage for why we even bothered to do this. This work was done in collaboration with Nimbus Therapeutics, and I'm very grateful to them for allowing me to share unblinded slides with you today, because it lets me really dig into how we use these models to design the next rounds of compounds. So I'm going to talk to you today about cytochrome P450 inhibition, which is something that when your compounds are inhibiting cytochromes, you can cause drug-drug interactions. So cytochrome P450 enzymes are responsible for the vast majority of small molecule metabolism in the human body. Most molecules are metabolized by less than a dozen of these different isoforms of P450. And like I said, inhibiting these enzymes can result in drug interactions, because now you're changing the way that other drugs that might be metabolized by those isoforms are being cleared from the body when they're co-administered with the drug that you're developing. P450 enzymes contain an iron chelated heme cofactor that catalyzes the addition of an oxygen to the various substrates. The kind of typical bad offenders for CYP inhibitors are nitrogen-containing heterocycles. It's a little bit small, but you might be able to see ketoconazole, which I've drawn the structure of for here. See that we have this imidazole ring that is directly coordinating to the heme. This is 3A4. Furthermore, the role of P450 enzymes in metabolizing xenobiotics leads them to be notoriously promiscuous binders. These binding sites are large, they're flexible, they like to scoop up grease and start chewing on it, and creates many opportunities for various inhibitors to bind and inhibit their activity. So we're working on this series. The primary characteristics are we had this aryl sulfonamide. We're going to talk about this quite a bit later on in the talk. We have this cyclopropyl group. This could really be a number of different aliphatic R groups. Then we had this thiazole with an amide linker, and this ethoxypyrazine ring hanging off on the end. Most of the SAR that we were interested in exploring as we were heading into lead optimization was around this R group hanging off of this methylene linker. Early on, we had profiled NTX423, which is this scaffold with a hydrogen hanging off here. We were looking at CYP inhibition and kind of the usual panel of the various isoforms that you check. The initial experiments that we were doing were percent inhibition at 10 micromolar of compound concentration, testing 2D6, 2C9, 2C19, 1A2, and then two different substrates of 3A4, midazolam, and testosterone. When we got this data back, we were pretty happy with it. Percent inhibition less than 50% is great. That means that you're very likely to be around 10 micromolar IC50. When you get the full IC50 measurement, we had a little bit of a concern around 2D6 and 2C9 for these, but nothing so major that we wanted to throw up a flag and address that to begin with. So we were very surprised when we made NTX 871. We hang a ethyl group off this carbon, or this R group. And we found that we had gone from being a nearly 9 micromolar inhibitor of 2D6 to now a 78 nanomolar inhibitor of 2D6. This is a problem because while you might not hit 9 micromolar concentration when you go into humans, and that's your free drug concentration exposure, you might very well hit 78 nanomolar, and that could be a problem for causing drug-drug interactions. We also profiled a number of other compounds that we had developed on this series, this methoxy group, this bridged morpholine, and a THF ring. And we were somewhat gratified to see that these various other analogs didn't pick up too many other CYP inhibition liabilities, but we really weren't solving CYP2D6 inhibition by adding some additional polarity. Even introducing a weakly basic group only mildly addressed the issue. This is still somewhat concerning for us. So we thought about, okay, what can we do from a structural perspective? We looked at the CYP2D6 structures that are out there in the public. We did this work a couple years ago. So at the time, there were 10 public PDB structures. Our criteria were that we wanted wild type human CYP2D6, and we wanted a ligand bound. And when we looked at these structures, we were moderately encouraged by what we saw. So of course, we had the heme in all of these structures. We saw a little bit of helix motion up here and some moderate loop motion here. This type of motion we thought was maybe not going to be trivial for when we're trying to predict the binding mode of our compounds in these binding sites. But certainly compared to some of the other CYP isoforms, we liked what we saw here compared to what you see for some of those others, especially stuff like 3A4. So we set about using induced fit docking, and we ran this in parallel across all 10 of these public structures. We also allowed for both direct heme interaction as well as water-mediated interaction. So we actually ended up running this on what was basically 20 different structures. So we took our workflow for IFDMD, where we took the prepared structures of the off-target, CYP2D6 in this case. The various ligand conformers that we had generated were aligned to a reference, to the reference ligand in the binding site by pharmacophore features. And at this point, crucially, we're retaining the protein clashes because we then use those clashes to identify which side chain should be refined as part of the induced fit part of the IFD. We then dock the ligand of interest. I should say that in this case, we took our most potent compound, which was NTX-871 to do this work. We then took all of our dock poses. We ran 100 nanoseconds of molecular dynamics on each of those poses to reduce or to relax the system, and then scored those poses with W-score and metadynamics. We took everything that came out of here into what we called, you could call it a prospective evaluation. It's really a whole data evaluation. We took some of our SIR. We ran FEP on all those different poses to see what the retrospective performance looked like across that set. The poses that looked reasonable in that retrospective analysis, we then looked at by eye, and we looked through the binding poses and said, does this make sense with the SAR that we're seeing on our project ligands? We then took a small set of those compounds, of those poses, and we'll get into what those looked like. And we took a much larger set that we had been generating experimentally while we were doing this work and said, okay, now that we have some binding poses that look pretty good with this small retrospective set that we had initially, can they recapitulate the SCR that we're seeing experimentally? And all of this was really to identify a binding pose that might give us some either predictive power or at least generate some prospective hypotheses for us to test as we go forward. So you've all seen this slide. I don't really need to go through it. I included one just to show you this is the movie that we were trying to get work earlier, but also to say that we chose to use relative FEP here for a couple different reasons. One, these are congeneric ligands, so we wanted to take advantage of that. They were really only perturbing a small number of R groups on this set. Also, we were concerned about modeling interactions with the heme. We weren't sure if we'd be able to do that. And we thought that relative FEP might be able to get us around having to deal with that. And to remind everyone, we did this maybe 4 years ago. So none of the advancements in the force field that you've heard about today were available to us at the time. So we were, I would say, somewhat disheartened to see that we had generated really, we'll started with 4 quite disparate binding modes that when we looked at the retrospective performance over that larger set of about 30 compounds, were giving us somewhat similar RMSE. This is the pairwise RMSE for that retrospective set, as well as similar R squared. Some of them were noticeably worse than others, I would say, in terms of errors or poor R square values. But these binding modes are all fundamentally different from each other. We've got R groups that are oriented in different ways from each other. We had this guy that wasn't even interacting with the heme group. And we also had some water-mediated interactions. And as we were looking through these, we realized that we had been modeling this sulfonamide in the deprotonated form, which is important for the on-target potency that we were dealing with. But we realized that it's probably not a guarantee that it's binding the same way. And we went back and we repeated this work. So again, that's another 20 sets of IFDMD calculations with the protonated form. And we got to model E, which again, even though it had a totally different protonation state than the rest of these, on the same set of compounds, was giving a similar pairwise RMSE and R square. So we took a look at these and we started to dig into the poses and say, okay, well, are there any actionable hypotheses that come out of these that might help us distinguish between which of these binding modes is right? So diving into it, I'll give it away from the get-go. Model E is the one that we ultimately settled on. The really key experiment was dealing with the protonation state of this sulfonamide. We were able to really test this hypothesis, and it worked out quite nicely for us. But just walking you through some of the key features of the predicted binding mode, we had a hydrophobic pocket here that was sensitive not only to the polarity of the substitution that we were sticking to that pocket, but also the stereochemistry at this carbon. We had both the R and the S enantiomer for here, so we were able to kind of probe the sensitivity there. The model proposed direct heme coordination via the pyrazine. That wasn't all that surprising to us, but it did make quite a bit of sense that we saw many predicted poses that had that. And then we also identified that this sulfonamide in the neutral form was interacting with a glutamate in the binding site. And that was something that we thought we could take advantage of with actionable follow-up designs. So while we were looking at this and talking this over with our medicinal chemistry colleagues, one of them kind of pointed at the structure and said, doesn't look like the other enantiomer is going to fit with this glutamine sitting right there. Why don't you go back and test the distomer? We hadn't been testing these compounds because they're much less potent on target. And so we had only moved the more potent compounds forward. So we took this compound, which is a 78 nanomolar inhibitor of 2D6. We ran the FEP on it. We predicted this as a micromolar binder. We were reporting only categorical predictions for these because we really weren't sure if we even had the right binding site or binding mode rather. We were very gratified to see that these compounds came back as a 3.3 micromolar inhibitor. This was particularly powerful for us because this was a way to test these hypotheses with a compound that had the same log D. So we didn't have any confounding factors where we were increasing or decreasing the lipophilicity of our compounds because these binding sites like grease. So there was always going to be that kind of factor to deal with. Like I said, we also wanted to probe whether or not changing the acidity of this sulfonamide might help us address this 2D6 liability. So we thought, if we make this more acidic, oh, I did it too. If we make this more acidic, there's going to be a state penalty to protonate and interact with that glutamate. It may either have to shift binding modes or maybe not want to bind at all. So we took a compound that was nearly 200 nanomolar binder. The PK, this says it's predicted here. This is actually an experimental value of 7.99. So very, very weakly acidic. And we designed a compound that had instead of a pyridine ring, a phenyl ring. Instead of a cyclopropyl, we had switched to a CF2. So we had now decreased or increased the acidity rather of the sulfonamide to 5.9 pKa. Again, predicted this compound to be a micromolar binder, and again, very gratified to see that we've gone from 200 nanomolar to a 4.2 micromolar inhibitor. Which brings me to something that I swear I didn't coordinate with ABBA, but this is something that was really important to us for both on-target and off-target predictions, was being able to predict the PK of these sulfonamides correctly. As we were modeling these compounds, both on-target and off-target, we were modeling both form of these compounds and then doing a pKa correction. This was done before we had the groups panel, so this is a little bit more painful than it is now, and so very, very grateful to see that kind of evolution in the technology. And so we were able to do these pK predictions with QM calculations using Jaguar. We knew that sulfonamides were not particularly well predicted using kind of Jaguar out of the box. We were able to get to really, really nice performance. This is the prospective performance of 14 different aryl sulfonamides that were predicted, and then we got measured pKa's for them with an RMSE of 0.65. Those are the bootstrap confidence intervals. We did this by just using a simple linear correction on the QM calculations. We used 2 program data points that we had measured early on, as well as 3 public data points. None of those data points are on that slide. So we were very happy with this. We really needed to do this in order to get the population and solvent for the protonated and deprotonated form correct. And so you might be able to see that as we moved from something like NTX 298 with a pK of 7.9 predicted around 7.7, moving to NTX 707 with a pK of 6. These are all the measured values. These are the predicted values. Predicted 5.9. We were able to maintain the on-target biochemical potency, as well as, although we did lose a little bit of the off-target selectivity, this is not for a CYP2D6, this is for a different off-target. We were able to maintain the subnanomolar cell potency in this compound in 2 different cell lines, and we were able to identify that this compound would be a micromolar, in CYP2D6, and this is something we were much more comfortable with. This is predicted to be kind of in the borderline, high hundreds of nanomolar, low micromolar range. For this compound, we also were able to design NTX 249, which goes from a pyridine to a pyrimidine, decrease the pKa by quite a bit, and as well as basically totally dialing out CYP2D6. So this is really nice for us to see. We did lose a little bit of potency, but we were able to pick up some selectivity along the way. So this was, again, very interesting and created a number of different subseries for us to work with as we push deeper into lead optimization. We also were able to again, confirm our initial suspicions that the ethoxypyrazine was one of the contributors to why we had this CYP2D6 inhibition liability. We suspected early on that modeling changes to the heme interaction would be outside of the domain of applicability here. We had really only one other kind of piece that we could replace the ethoxypyrazine with, which is this pyrazolopyridine bicyclic ring system. When we ran the FEP prediction, this is predicted to be about as potent as the ethoxypyrazine, even though it is, again, basically totally unmeasurable in our assay. This is something that we would really love to see, and we're excited to see some of the changes coming to the way that we model to model interactions with metals, because this would have been nice for us to do on the project. We could really design different warheads here and kind of leave and still use some of the other pieces on the series that we had. For better or for worse, we were really only locked in. We really only had these 2 options. The on-target potency didn't allow us very much flexibility here. So this wasn't such a huge loss for us, but it was, again, pretty interesting to see. So some of the key takeaways. This off-target binding mode prediction combined with free energy calculations really enabled us to rapidly generate design hypotheses to address a key liability on our lead series, and we had a really big impact on project progression. I think I alluded to, we also were able to spin out a number of different sub-series that we hadn't previously been considering as we progressed into lead optimization. One of the things that surprised us was that even though we had very disparate binding modes that were very, very different to us, they were still producing similar retrospective performance on that initial smaller set of SAR. So it was useful for us to really dig into those poses and generate these hypotheses that we could then use prospectively to not only narrow down what binding mode we should be looking at, but also drive the project forward. And with that, I just want to thank the team that worked on this. So like I mentioned, this is a collaborative effort with Nimbus Therapeutics. So I want to especially thank Josh and Lilu, who were the key biologists and medicinal chemists working on the project for taking, I think, a number of risks on some of the modeling and hypotheses that we were suggesting, as well as the team at Schrödinger. The modeling was done by myself, Kevin DeMarco, Andreas Ferris. Mats was instrumental in the PK predictions, and Ed Miller automated the IFDMD workflow for us to be able to explore the really large number of calculations that we needed to get here. And with that, I will take questions.
Thanks, Steve. We have time for a couple of questions over there.
Yeah, that's a great question. So we probed this a little bit. We used when we got that binding mode, we actually ran WaterMap on it just to kind of get a sense. We already had an idea from the SAR that it was very likely we were displacing some high energy waters. That bore out in the WaterMap. So I think that was part of it. You also may have noticed that in some of our binding poses that the aryl sulfonamide was had some freedom to rotate around in the binding site. I also suspect that having a substituent, even and the greasier the better, was locking it in so that that sulfonamide could then kind of reach over towards that glutamate. So I think it was kind of a both and, but the high energy water is definitely why we saw a preference for the greasier compounds. As we went to weakly basic and even more strongly basic compounds, you did start to see the CYP2D6 activity kind of fall off. Yeah, so we didn't have MET ID. Just really from looking at the compound and looking for where is there an aromatic nitrogen that's kind of unobstructed. That was why we really keyed on that, and we that was what we expected to see, but we weren't sure if it'd be water mediated or not. We could, there are spectroscopic methods that you could use to really probe some of that stuff that I think are really interesting. So I'm not fully sure about MET ID. We didn't have it available to us at the time, and it's sometimes can be more confusing than it's worth when you're digging through that data.
All right, let's thank Stephen one more time.
Thank you.